So here's another example. I'm going to do number 20. So again, you see the minus there indicating that this is a hyperbola. This time around, it's the x squared in the front and the y squared takes on the minus. So this is a sideways opening hyperbola. And I have to remember here that my center is at 6 and -4. And then the denominators are 3 squared and 4 squared. So I'm just going to jot these down. And before I actually plug in numbers, I'm going to have to turn this one back to sideways hyperbola and the, let's see, the focal points. I have to turn these here. Oops. There we go. Okay, now I'm going to plug in the numbers. So I have a 6 over here for the H, I think it was. There we go. There we go. And K was a -4. There we go. And then I have a 3 and a 4. So 3 and 4 here. And there's that hyperbola. Again, if we were to graph it by hand, we would start with the center and then do the box with the A values left and right and the B values up and down. And then we would draw in the diagonals, which are the asymptotes, and then we would do the hyperbola here being the vertex, and then this being the asymptotes, and the same thing on the other side. And then if you put the circle in, yeah, we get the foci in there. Now, Symbol Lab is also pretty slick, and this one here is already prepared it. All I had to do was Google Symbol Lab Hyperbola, and I came up with this one here. You see I already plugged it into my liking. I can easily see that the center is 6 and -4, and that these two box sides are +-3 and +-4 in the horizontal and the vertical. And when I click go, then it's calculating this one here. It's going to tell me where the center is, 3 and 4. And when I'll scroll the way down, then I can see that this one is the hyperbola. These are the asymptotes. Here they didn't draw the entire box, but they just show us that this is the way the box would look like. So a little of sides. And then they have these kinds of different menu items here that I can click on, asymptotes, so it calculates what the asymptotes are. And here they are. They are, of course, straight lines. You see slope times x plus y-intercept. And then here they are. That's, of course, the same thing. I was hoping that they would all do it at once, but we'll have to click on each individual to figure those out. And, of course, they all go back to this table here in the book for the general case, this one right here. Okay, a couple more things that I found. So if I scroll past all these exercises, then here, of course, I zoom in on the physics and astronomy stuff. I showed art earlier, but here is physics. So positively charged particles repel each other. So I think, let's see, where did I put that one? This one here, yeah, right here. So this one is where you would have what is called a target nucleus, which is positively charged, and then you have another positive particle which approaches it very fast, but of course it's repelled because like charges repel. So due to its inertia, it wants to fly on, but it's repelled from this positive particle here like this, and then it goes off here, and now it's far enough away that it's not repelled so much anymore and almost follows a straight line. And you can see these are the asymptotes here. And then, I don't know, the focal point is probably somewhere here. And then you can see the hyperbolic shape for this one. Another one would be hyperbolic orbits. As discussed earlier, orbits are usually elliptical, but that's true, or almost circular even. That's true for planets and moons and satellites. But there are few objects that actually do have hyperbolic orbits, and those are some comets, not all comets. There's a number of comets who do have elliptical orbits, very elliptical. But this one apparently is a comet that has a very hyperbolic orbit. It comes from either the Oort cloud or the Kuiper belt, which surround the solar system way out there. And it comes in, and then it goes out and is never seen again. So it only enters the solar system once, leaves forever. There is a famous, actually, object. It's not a comet, but it's a interstellar object called Umuma, I guess. I should have learned the pronunciation. And if the object is fast enough and astronomers can measure that, how fast it is by analyzing photos, why does this not get in focus here? That's interesting. Seriously. Anyway, that's not a great image. Anyway, it's fast enough, and then they can deduce that, hey, this didn't come from our vicinity. It came from somewhere else, from another star. So that's what happened to this particular object. And then I have this one here. We have seen this one here before, PHET, still the solar system app. And here I chose the hyperbolics. And what they did is they have 3 comets here that are fast enough that when I hit the start button, we can see that they describe these hyperbolic orbits. And they just go in once into the solar system, and then they go out and never be seen again. Let me reset that here, because if I do this one here slow enough, let's see, I haven't tried this before. So let's see what happens if I make them slower. I hope they're not going to crash into the sun here. All right, let's see. Okay. Nope. Ooh, it's still hyperbolic, huh? It wasn't slow enough. I'll try it again. It's only because I want to, right? So a hyperbolic actually might become an ellipse. I think the pink one is going to come back. Yeah, there it goes. It's just a little bit off the screen here. There it comes back. So it depends on the velocity with which it approaches the sun in this case. And there, I know it looks like it flies into the sun, but I think they turned off the, oh, the other one comes back too. It turned off the collision possibility in this applet here. So yeah, if you change the parameters of an orbit, a hyperbolic orbit, the green one is coming back too. If you change the parameter of a hyperbolic orbit, make it slower, then you would also change the nature of it, and the hyperbolic orbit becomes elliptical orbit. That usually doesn't happen because of its inertia, but actually there is a famous example. It's the comet Shoemaker-Levy 9, which was on a hyperbolic orbit, got too close to Jupiter back in 1992, I believe, was captured by Jupiter, and actually got into an elliptical orbit. And actually I should pause here and look that up, but here it is, comet Shoemaker-Levy 9, there we go. And that's actually the one that crashed, that actually split up into lots of pieces of fragments of comet and then plunged into Jupiter. And we can see here on the far side of Jupiter, these are the explosions of these comet fragments hitting Jupiter's clouds. And then here we can see the impact sites. Because Jupiter is a planet totally covered by gases and clouds, these here dissipated over time. You know, they didn't form craters because these are gases and clouds. And yeah, there they are again in another nice picture. And yeah, Jupiter actually caught that hyperbolic comet that then got into an elliptic orbit and then crashed into Jupiter. All right, and that's what I wanted to tell you about hyperbolas for this section.